Hello, and welcome to this video discussing how best to partition your data when using linear classification on EEG data. So I'm going to start off by contextualizing defining partitions by describing a potential confound in linear discriminant analyses, and this confound is overfitting. In short, overfitting is a fitting of an ungeneralizable hyperplane to data, and by ungeneralizable, I mean a hyperplane that does not help classify stimulus categories when applied to another data set, or does not help classify stimulus categories when applied to a population at large. Take, for example, what we've got on the slides, a situation where we have 3 trials. So we've got a yellow trial, a blue trial, and another yellow trial. We can pretend that these are trials where you've been presented with a yellow stimulus and a blue stimulus. Now, if we try and fit a linear classifier to this, we're not going to have much luck, as they all sit on a gradient, and there's no real way to separate these categories out linearly. However, maybe we can try and expand it a little bit. We can go, well, let's use a non-linear one, see how that fits. And because we've used a very small amount of data, then if it's perfectly in fact, we can just draw this little guy, this dotted line here, and go, yes, wonderful. It fits absolutely perfectly. However, will this generalize to a complete data set? Well, clearly not. If we look at the big picture here, it is actually a linear division here. We've got the blue guys up here, we get the yellows up here. There's obviously a little bit of error, but that's always going to happen. And if we were to draw a non-linear one around here, then really actually it's going to be about chance. So despite fitting the data very nicely into our training set, it clearly doesn't generalize. And this is the problem of overfitting. So what can we do to fix this? Well, the easiest way here would be to increase the number of trials in the data set. If there's more data in the training set, then the ratio of the signal to noise increases and the likelihood of fitting to noise drops. This is always something to consider when trying to partition your data, and perhaps the first protocol when trying to debug why your classifier is giving you weird results is because of how you've partitioned your data. Perhaps there's overfitting going on here. So, for example, perhaps the data is partitioned such that one partition consists of data from the first half of the experiment, and the second partition consists of data from the second half of the experiment. Well, then there may be differences in the 2 partitions based on behavior or cognition that is correlated over time. In the first half, participants might be really energetic. In the second half, they might be tired and lethargic. This will be reflected in the EEG activities, such as neural activity or maybe muscle artifacts. People move about a bit more. And the classifier may fit these characteristics in some way, shape, or form. So we can imagine a situation where you've done a great job classifying the training data on the first block, but because people have changed in their energy, their movement, when we try and apply this to a second block, there's some error going on. There's been some overfitting to characteristics in the first data set, so it doesn't generalize to the second data set. Now, generally speaking, overfitting can take many forms. It can be a little difficult to tell why the data is overfitted, and even if the data has been overfitted. So because of this, I'd always recommend you see how the output of your classifier varies based on your approach to partitioning. If the effect is consistent across methods, then brilliant. If it seems very substantially, then perhaps it's time to look further into your data and see if you can understand where this weirdness is coming from. And this is what I'm going to talk about now. How to partition your data to see if your fit is, or your classifier fit, your hyperplane is a good fit for data. So the first way to consider how to partition your data, we're going to really look at this k-fold classification. So splitting your data into k-folds, where k is an integer value of your choosing, and seeing how it impacts your data. So generally speaking, a small number of partitions leads to fewer trials in the training data set and a greater chance of overfitting. So if you've got a data set here full of, I think that's about 12 trials, and we say we're going to have 2 folds, so that's k is 2, 2-fold classification, then we can split it into 1, split it into 2. Now we can train on the training set and apply to a test data set, and we can swap that round to, and well, it's a very simple, quick way to do it 2-fold. However, because we've got such a small number of trials in the first fold and in the second fold, but it doesn't tend to generalize very well. There's a risk of a small number of trials in the data set, in the training data set, leading to overfitting on this training data set. However, there's ways we can defeat this. So if we were to partition the data into 4 partitions, so now we've got 4 partitions, each of 3 trials, then we can combine some of these folds into a larger training data set. So we take, in this case, fold 1, fold 2, and fold 3 to make a training set of 9 data points and apply it to a testing set of a smaller sample. So with more trials, that means there's less chance of overfitting on the training data set. So when you generalize the classifier to a testing data set, there's less of a risk of overfitting. However, there's always a trade-off going on here. You can essentially choose K to be whatever you like, and the larger K gets, the greater the size of your training data set, and there's a smaller risk of overfitting the data. However, it's also going to take longer to do. So if you, in this case, where we've got 4 folds, then we have to do the classification 4 times. We have fold 1, 2, 3, and then we've got fold 1, 2, 4, testing on data set 3, fold 1, 3, and 4, testing on fold 2, and fold 2, 3, and 4, testing on fold 1. So that's going to take much longer than the 2-fold classification, where you only test on 1 fold and apply to another twice. So however many classifiers you need to do, K not only tells you the number of folds in the data, but it also tells you how many times you need to train the classifier and apply it to the data set. So this is always something to bear in mind as well, that while a small K is 2, you run the risk of maybe overfitting because you've got small numbers in your each fold. Larger folds, larger Ks means you get better fitting, but also increased computational cost. So this is always something to just bear in mind when you're deciding how to partition or how many Ks to include in your folding. And then the other decision to make when you're defining your partition is how to choose where to fold in your data. And this can be split into one of 2 ways. Either you can split the data in an ordered fashion based on logic or some rationale based on the data, or you can split them up randomly. Ordered partitions involve breaking the data set up based on some aspect of the experiment. For example, you can split the data based on block number. So you could train on block 1, apply to block 2, and then flip it round. So you train on block 2 and then apply to block 1, as we've just got explained here. This is a really straightforward approach. It doesn't take much time to implement or compute. If we go back to the idea of how many folds includes the data, but it makes assumptions about the data. Namely, that the noise is consistent across the 2 blocks, and therefore the weights can be generalized across the 2 blocks without issue. However, this isn't the case, and as I mentioned earlier, participants might get tired over the course of the experiment, or may get a better understanding of the task as the experiment progresses, meaning the noise between the blocks may vary, and therefore the classifier might not generalize across to other testing data sets. An alternative ordered approach would be to split trials based on whether they're odd or even. Again, this is going for a 2-fold design, so you can get trials 1, 3, 5, 7, 9, and 11, and put 2, 4, 6, 8, 10, and 12 into separate blocks. So this is again another ordered approach, as you know exactly how to reproduce that partitioning. But again, it's still got small trial numbers. But the advantage of this over the block approach, splitting it based on block number, is that now there's an even distribution of trials across the time course. So if participants are getting more tired towards the end of the experiment, or if participants are getting better at the task, then this is counteracted because they're evenly distributed between the 2 blocks. So ordered folds are really nice because they're quite fast to compute, and they're also very easy to reproduce. However, you always need to make some sort of assumption about the data if you're going to choose to order your classifiers. So the alternative you can take is to use random folds. And this is where you just use a random number generator to split the data between the folds, and then train and test it on the classifier and repartition the data randomly. Unlike ordered approaches, random folds make no assumption about the noise in the data. However, it comes at the cost of computational efficiency. If you do a single random partition, it's not very easy to reproduce in a separate analyses, or you want to reproduce it for another paper or whatever, the fact that you've done a single random permutation just means you're not going to be able to get the same result each time. And therefore, the findings will vary between each random partition. So it's best to repeatedly randomly partition the data, say 100 times, and then take the mean classification output across these permutations. And this will obviously take a little bit more time than the ordered partitions because you are having to repeat the process. But it also ensures it's a little bit more reproducible than just using a single random partition. So the random folds have this benefit that it makes less assumptions about the data than ordered folds did, but it also takes a little bit longer to compute and is a little bit less reproducible. So again, like deciding how many folds to put in your data, this decision where to partition your data is really up to you. And perhaps it's best determined by the computer hardware you have available to you. If you've got really fancy computer, really nice RAM to hold lots of data, then perhaps the random fold approach works really nicely. But if you're kind of strapped for time, computer processing power, then ordered folds may be a little bit more handy here. So the last thing I'm just going to point out when talking about partitions is the idea about balancing partitions. So on the previous slide, we've had some examples of different partition patterns, and we've all had one issue. And that is that these partitions haven't balanced the trial numbers between the two categories. So we can kind of consider this issue with this plot we've got here. If we split the data into two folds, each of 6 trials, then if they're unbalanced, then we might get 5 yellow trials and 1 blue trial. And again, we can fit this wonderful classifier for data. And it seems to really separate out the yellow stimuli from the blue stimuli. But despite there being more trial numbers in the partition, and therefore reducing the chance of overfitting to a small number of data points, the fact that there's still only one single blue trial here means it's still very easy to overfit the data. So when you're partitioning the data, you need to remember to balance the trials. You need to make sure there's an even number of trials in each condition, because then you're not going to run into issues with overfitting to a single data or a single category data point in your data. Because if we can consider the testing data set, such a classifier doesn't generalize very well at all. So that's just a little whistle-stop tour on how to partition your data. I hope it's been useful, and then I'll see you in the next video.